Welcome to CS571 operating systems. So in this video, we'll be talking about paging and page tables. But before really start talking about paging, so let's first go over what has been discussed in our previous lecture, which is memory segmentation. And this will be served as a motivating factor that really motivates the need for fine-grained paging and fine-grained page table design within operating system, okay? So recall that in our previous lecture, we've discussed these following three following fundamental approaches of performing basically virtual memory accesses, converting the virtual memory accesses to the physical memory accesses, basically translating the virtual address into the physical address. And the first basic approach is called static relocation, where it requires a piece of software to perform this static and offline rewriting for each and every virtual address that has been generated by the compiler into the physical memory. And the ultimate goal of static relocation is, to avoid the conflict between two different programs that are running concurrently with the same piece of code. So basically to enable effective and correct memory sharing between different programs. Obviously, this is costly because before you run the program, you need another different piece of software, for example, the loader, to perform this static and offline rewriting operations. So this is the first basic approach, static relocation. And the second approach, which is slightly advanced against the static relocation, is called dynamic relocation. Within the category of dynamic relocation approach, we have these two different variants. And the first variant is a baseline case, which is called Bayes method. Within Bayes, the operating system always maintains a single piece of information, which is a Bayes address, so that whenever translating a virtual address into the physical address, the operating system would just simply apply a virtual offset on top of this Bayes address to translate this virtual address into the physical address. So this is the first variant, which is a baseline case. And the second variant is called Bayes and bounds, which is a slightly advanced version on top of the baseline case, which is Bayes. So in Bayes and bounds, just as its name suggests, the operating system at runtime maintains one more piece of information. Besides in the Bayes register, the Bayes address, it also maintains an upper bound, which is called bounds address. So whenever the program performs a memory access operation, the operating system at runtime will always check whether the calculated physical address is falling into the legal range that is confined and defined by the Bayes and bounds of these two values. So these are the two different variants of the dynamic relocation approach. Dynamic relocation approach is not flexible and incurs memory, it's not that efficient in terms of memory utilization. So that motivates a third approach, which is called segmentation. Segmentation, again, as the name suggests, is to partition the whole, either the virtual memory address space or the physical, both the virtual memory address space and the physical memory address space, into relatively finer grained pieces. And each and every such memory partition is called a segment. And for each memory segment, the operating system maintains a pair of Bayes and bounds values to basically confine the memory accesses for each and every memory segments that belong to a particular running program, a particular running process. So this is segmentation approach. Okay, so let's further zoom in and see how segmentation approach works. So in this slide, it shows a really simple example of segmentation. Assume this targeted virtual address space has 10 bits virtual address, and assume in order to support fine-grained segmentation, you need to logically partition a virtual address into two parts, the high bits parts and the low bits parts. And in this example, assume the high bits part consists of 2 bits. And these 2 bits, in theory, could be used to index into as many as 4 different memory segments, right? 0, 1, 2, 3. These 4 different memory segments. And each segment has its own index ID, ranging from 0 up to 3. Okay? Assume in this example, the segment 0 gets mapped to the very first memory segment, which is the combined code and data segment. And segment ID 1 gets mapped to the heap segment, which is dynamically, whose size is dynamically adjustable. It could dynamically enlarge, could dynamically shrink, depending on the behavior of the running program. And the third segment, segment ID 2, gets mapped to the third memory segment, which is called stack. And stack consists of those different function stack frames that stacked on top of each other. Okay. So in this slide, on the left-hand side, it shows the virtual memory layout. As you can see, this virtual memory is further partitioned into a total number of 16, let's call it fine-grained memory blocks. Okay, and it has the total memory size range from the low bits 0 in hex form all the way to 400. Okay, and this 400 memory capacity further partitioned into 4 coarse-grained memory segments, and the starting address of each memory segment is labeled over here, a 0, and 0x100, 0x200, as well as 0x300. Okay, so in this slide, it shows where exactly the 3 different pieces of memory segments gets located. So as you can see, the very first code and data segment is located within the first memory segment, within occupying only one single memory block. This is the code and data segment. And the second memory segment, which is called the heap segment, is located with the starting memory, a virtual memory address of 0x100 in terms of hexadecimal format. Okay, so this is the second memory segment. And the very last, the third memory segment, is called stack memory segment. It's located at the bottom half of the virtual address space. Okay. In this slide, at the right bottom corner of the slide, it shows a so-called memory segment table. Okay. Segment table. And whenever you want to perform a virtual address to physical address translation, you always will need to consult with this memory segment table to be able to calculate the final physical address. So this table in this particular example has 3 elements associated with those 3 memory segments, code, heap, and stack. And each memory segment, it keeps track of 2 basic information. The first one is a base, then the second one is bound, right? So within the current information, which of these 2, base and bounds, is known ahead of time, right? Okay, so it's the bounds value is known, because the bounds basically just define the size, the length of the corresponding memory segment. As you can see, the code memory segment, it has, if you take a look at over here, it just occupies one single fine-grained memory block. So it has a bounds value of 40, OX40. Okay, so the next memory segment, heap segment, because it occupies, 3 contiguous fine-grained memory blocks. So it's basically 0x40 times 3 gives you 0xC0. Okay, so this is its bounds value for the second heap segment. So similarly, you can easily calculate the size, the bounds value of the third memory segment, which is stack, since it occupies like 2 consecutive memory blocks. So its bounds value is 80 in terms of hacks. Okay, so far, what is not known is the base value, because base value is the physical address, which is not known right here. So we still further need actual information, which is exactly its physical memory layout. Okay, so over here, this slide shows its physical memory layout, and also shows how exactly the virtual memory segment gets mapped to its corresponding physical memory segment. Okay, so over here, the unknown information is provided, which is a base value. So base, because the base value is always physical address. So the very first segment code, if you take a look at where exactly it locates within the physical address, it's located over here, right? So it has a base value of 0x400. Okay, and the heap memory segment is located at the very beginning with its starting address starting from the very first byte within the physical memory. So its base address is 0. Okay, so how to translate a provided virtual address into the physical address is by applying the simple equation provided at the very bottom of the slide. So the physical address is, the sum of the virtual offset plus the base physical address. Okay, so basically what it means is you apply the virtual offset on top of the base value to translate the virtual address into the physical address. So in this slide, it shows an example of how exactly you translate a virtual address into the physical address in this example. Okay, so on the very left-hand side of the slide, you get a virtual address, which is 180 in hex. So this is somewhere in the middle within the second memory segment, which is heap segment. Okay, so in order to calculate the corresponding physical address, you need to first extract the virtual offset from this virtual memory address. So obviously, its virtual offset is 80. So how to calculate that is you just subtract 100, which is its base virtual address, from 180, which gives you 80, which is highlighted using this red color. Okay, and then you further apply 80 to the base address, which is 0, to calculate its final physical address, which is 80. Okay, which is somewhere over here, somewhere in the middle within the first memory segment, within this the first memory segment with respect to the physical memory location. Okay, the next question you may ask is, so the heap memory segment is dynamic, its size is dynamically adjustable. It means that it could at runtime enlarge or shrink freely. So what if it's just located within the memory range, right underneath, right below it has another memory segment, right? In this example, it has the code segment. What if the heap segment want to dynamically enlarge its capacity? How to perform this operation? Okay. So in this case, you either need to migrate the heap segment somewhere else where you have a large enough memory capacity to accommodate this growing demand, or you just migrate away the underlying the memory segment that right below it. In this case, the operating system picks to migrate the code segment from its original location in the middle, somewhere in the middle of the physical memory layout to the very bottom, okay? And this is after the code segment has been migrated. But here, note here, you need to, after the code segment gets migrated from the middle of the physical memory into the bottom of the physical memory. So what the operating system needs to do is needs to update its base value. So this was before the migration was done, right? It has a base value of 400. This is after the migration was done. It has the updated base value, which is C00, okay? And then the heap memory segment could be grown downwards, and at the same time, you need to update its limit, its bounds value from its old size, which is C0, to this newly updated size, which is 100, okay? And then, so this is how basically you support this the memory segment growing, okay? So that inevitably fall into this so-called dilemma where you must waste space, memory space, or waste the performance time, right? So let's first take a look at why, this segmentation-based approach gets to waste a lot of memory space. So in this slide, it shows an example of so-called external fragmentation. So what does external fragmentation mean? Well, so as we are talking about multi-program operating system where there can be multiple processes that are running concurrently within the operating system. So as processes are loaded and removed from the main memory, as processes come and go, the free memory could be broken into like many fine-grained small pieces, just as shown in the picture shown on the right hand of the slide. So those free spaces that are not used, are called memory holes. So those memory holes are essentially those block of freely available memory that could be used to accommodate small memory requests. Okay, but the dilemma is if the whole physical memory is having too many such small memory holes, so we fall into the dilemma, even though you have let's say you have a memory allocation request from some memory intensive applications. Even though collectively speaking, the aggregated size of those memory holes is large enough to accommodate this new memory request. But physically, each and every memory hole is randomly spread across this huge physical memory address space, so that none of them is large enough to accommodate this memory request. So this is the so-called external fragmentation issue, and it could be dramatically reducing the overall memory utilization. Okay, so this is one of the biggest problems of this coarse-grained memory segmentation mechanism. So this is the first situation where you end up wasting a lot of memory space, even though you are using memory segmentation approach to partition the memory into relatively coarse-grained pieces, partitions. And then let's take a look at the second dilemma, the second situation. If you don't want to waste space, then you end up wasting a lot of time. You add a lot of performance overhead for the runtime, for the running programs. Okay. So again, this slide, it shows, it illustrates what exactly means by external fragmentation. If you do parallel parking, so those cars are parked in parallel alongside the street parking. So those extra space between different cars are called external fragmentation. Okay. So ideally what we want is we want to minimize this external fragmentation to basically minimize the wasted memory that could not be effectively utilized by a running program, just as shown in this picture on the bottom half of the slide. You have compacted space between different cars. Okay, so let's next talk about the second situation where you must end up, wasting performance, wasting time. So if you take a look at the picture on the right-hand side of the slide, so as processes come and go, it leaves the whole memory with a lot of like randomly distributed small memory holes, right? So those are the memory chunks that could not be effectively utilized. So in order to better utilize those available memory space, you need to perform some compaction operations to migrate those already allocated piece of memory into the very top, okay? So as to come up with a huge contiguous free memory space so as to be able to effectively accommodate huge memory allocation requests from, let's say, some memory intensive programs. Just like, so at the right-hand side of the slide, it shows the memory layout after the memory compaction operation is done. Okay, you basically compact all the used memory chunks into one single contiguous piece, and so as to make those spread, small memory holes, collect all of them to make huge space. Okay, so this is one approach, one technique to improve the memory utilization, but it comes with a huge drawback, which is the significant performance overhead, because it incurs memory copy, memory paste to copy too many memory chunks. So that introduces dramatic memory overhead. Okay, so it's a most significant problem.